the cold bit deep in the Appalachian foothills. One settler carpenter learned that his first winter in eastern Kentucky in 1870, when his cabin floor froze solid every morning and never warmed above 30 degrees, even with a fire roaring 3 feet away. He had built his cabin exactly the way every homesteader in the mountains was told to build it: sill logs set on stone footings, tight mud chinking, standard and proven. By spring, he had burned through 3 cords of firewood fighting floors that felt like ice underfoot. Across the ridge country, families were losing the same battle in cabins built by the book and failing by the season. Over the next 2 years, this carpenter quietly applied an old-world method that kept his floors 35 degrees warmer and cut his wood use in half. What did he understand about heat and frozen ground that every serious builder today needs to know? The building method that trapped every homesteader in this cycle had seemed perfectly sensible when the first wave of settlers reached the Kentucky Ridge Country in the 1860s. Company promotional guides and frontier building manuals all recommended the same approach: set your sill logs directly on flat field stones or dig shallow trenches, pack the gaps with mud and clay, and get your roof up fast before winter. The reasoning appeared sound. Timber was abundant, but labor was scarce. Every hour spent digging deep foundations or raising elaborate supports meant less time for clearing fields, splitting rails, or hunting meat for the winter stores. Speed meant survival, and the ground contact method delivered a weather-tight shelter in half the time of more complex approaches. Across the high ridges, nearly every cabin followed this pattern. Chestnut or oak sills laid flat on whatever stones could be gathered, corners notched tight, gaps chinked with local clay mixed with moss or wood chips. The settlers who had arrived from Virginia and North Carolina brought this method with them, and it had served their fathers well enough in the lower elevations where winters ran milder and ground freeze stayed shallow. But the failures that winter revealed went deeper than cold floors. The settler carpenter watched his neighbor's cabin, built by a family from the same immigrant wave, suffer through problems that multiplied as the season wore on. The sill logs, pressed directly against stone footings that conducted ground cold, began showing dark stains by February. By spring, soft spots appeared in the wood where moisture had wicked up from the soil. Insects had found these damp sections, boring galleries through timber that should have lasted decades. The neighbor's wife complained of constant dampness, mold climbing the interior walls, and a persistent cough that wouldn't clear. Their cabin had become a trap for moisture with no way for air to move beneath the floor, creating perfect conditions for rot and sickness. More concerning was the heat drain. Even when the neighbor's fire burned strong, the cabin's interior temperature struggled to climb above 40 degrees on the coldest nights. The frozen ground beneath acted like a massive heat sink, pulling warmth down through the floorboards faster than the fireplace could replace it. By March, they had consumed nearly 4 cords of split wood, burning through their winter supply and forcing the man to cut green timber that smoked badly and gave little heat. The settler carpenter had watched these failures with growing unease, but he possessed knowledge that set him apart from his struggling neighbors. His family had immigrated from a northern European mountain region where timber construction had evolved over centuries to handle persistent cold and ground moisture. His father had been a joiner in the old country, and the cardinal rule of alpine building rang in the carpenter's memory: never let structural timber rest directly on soil or stone. The houses of his childhood had stood on stout posts or stone piers, raised clear of the damp earth, with air flowing freely beneath to keep timbers dry and floors warm. His observations extended beyond inherited wisdom. During his first autumn, he had worked alongside local Cherokee families who were constructing seasonal shelters in the valley bottom. Their summer lodges stood on short posts driven into the ground, lifting the sleeping platforms and storage areas well above the damp soil. When he asked about this practice, an elder had explained that ground cold and moisture would steal heat and rot timber faster than winter wind, and that proper building meant respecting what the earth would do to wood that touched it directly. These insights crystallized into a plan that seemed obvious to the carpenter, but struck his neighbors as wasteful foolishness. He proposed to build his next cabin on posts 4 feet tall, elevating the entire structure clear of ground contact. The idea drew immediate criticism from the county surveyor, a man who had guided settlement building for over a decade. The surveyor dismissed the elevated approach as over-engineering suited to expensive town construction, not practical frontier cabins where every stick of timber counted. The carpenter's neighbors were more direct in their mockery. They called his plan a waste of good lumber that could be sold for cash or split for cordwood. Some joked that he was building a cabin on stilts like he expected a flood. The social pressure intensified when word spread through the scattered homesteads. At the seasonal gathering where families shared news and traded supplies, several established settlers warned the carpenter against departing from proven methods. A Virginia family that had built 3 cabins in the region insisted that ground contact construction had served them without major problems, and that extra timber work would delay other essential tasks. A former mill owner argued that raising a cabin so high would make it unstable in windstorms and create drafty conditions that would waste even more fuel than a standard build. But the carpenter had seen too much evidence to ignore. Every ground contact cabin in the area showed the same pattern of problems: perpetually cold floors, excessive fuel consumption, early timber decay, and unhealthy interior conditions. The conventional wisdom that promised speed and economy was delivering neither. Families were spending more time gathering fuel, more money replacing rotted sills, and more days nursing illnesses that flourished in damp, cold cabins. His decision to proceed with the elevated design despite community opposition reflected a deeper understanding of building that went beyond frontier expediency. Traditional methods from both immigrant and indigenous sources had evolved to solve the exact problems that were crippling standard cabins. The 4-foot posts would break the thermal connection between living space and frozen ground. Air circulation beneath would prevent moisture buildup and timber decay. The elevated structure would prove more durable, more comfortable, and ultimately more economical than the supposedly practical alternative. The conflict was now clear: conventional frontier wisdom that prioritized construction speed against traditional building science that addressed the fundamental relationship between structure, soil, and thermal performance. The carpenter was about to demonstrate which approach would prevail when winter tested both systems against the harshest conditions the mountains could deliver. The carpenter began construction in late summer of 1870, selecting chestnut logs from a stand on the north slope, where slow growth had created dense, rot-resistant heartwood. Each post required careful preparation, starting with logs roughly 8 inches in diameter that he squared with a broadex to create uniform bearing surfaces. The posts needed to be precisely 4 feet in length, hewn smooth on all 4 faces to ensure even weight distribution and prevent water collection in rough bark grooves that could harbor insects or promote decay. The foundation layout demanded mathematical precision that separated this method from typical frontier construction. He marked the cabin footprint as a rectangle 16 feet by 20 feet, then established exact corner positions using wooden stakes and hemp cord stretched diagonal to ensure perfect right angles. At each corner and at 8-foot intervals along the longer walls, he excavated holes 18 inches deep and filled them with flat field stone arranged in stable platforms. These stone pads would support the posts while preventing them from sinking into soft soil or shifting during freeze-thaw cycles. Setting the posts required techniques the carpenter had learned from his father's joiner friend, an elderly craftsman who had worked on alpine timber construction before immigrating. The old joiner emphasized that posts must bear evenly on their stone foundations without rocking or high spots that would concentrate weight and cause splitting. Each post was fitted to its stone pad by careful trimming with an adze, creating a flat-bearing surface that distributed the cabin's weight across the entire stone platform. The joiner also insisted that posts be oriented with their growth rings running vertically, positioning the strongest wood grain to carry vertical loads, while minimizing the tendency to check or split under the cabin's weight. The Cherokee elder who had shown the carpenter elevated lodge construction provided different but equally crucial guidance about post installation. He demonstrated how to align posts so that their strongest faces oriented toward the prevailing winds, reducing the chance of wind loading causing structural movement. More importantly, he explained how to evaluate soil drainage around each post location. Posts set in areas where water collected would eventually rot at ground level, even if elevated above, so each post location needed to shed rainwater and snowmelt away from the timber. The elder showed the carpenter how to build small gravel collars around each post base, creating drainage that prevented standing water from softening the wood grain. Installation day revealed the precision this method demanded compared to standard ground contact construction. Each post had to be plumb in both directions, checked with a weighted string line, and maintained perfectly vertical while the sill logs were positioned. The carpenter constructed a simple but effective leveling system using wooden wedges and a water-filled trough to establish consistent height across all 8 posts. This process took 3 full days compared to the single day required to lay sills on ground stones, but the investment in accuracy would determine whether the entire structure remained stable through decades of seasonal movement. The sill log installation demonstrated why elevated construction demanded superior joinery skills. With posts supporting the sills 4 feet above ground, there was no opportunity to adjust for uneven bearing or poor fits by shimming with stones or soil. Each sill log had to be notched precisely to rest solidly on its supporting posts, creating full contact across the entire bearing surface. The carpenter used traditional mortise and tenon joints at each post connection, cutting rectangular slots in the sill logs and matching tenons on the post tops. This created mechanical connections that would hold the structure together, even if wood movement caused shrinkage or expansion. Winter testing began in December of 1871, when temperatures dropped below 0 degrees for the first sustained cold period. The carpenter had prepared measurement methods learned from his immigrant joiner mentor, who had emphasized the importance of documenting performance to validate construction decisions. He bored small holes through the cabin floor at strategic locations and inserted wooden dowels that extended into the airspace beneath, allowing him to measure air temperatures in the gap without opening large holes that would affect the system's performance. The results confirmed what traditional builders had known for generations. On the coldest night, when ground temperature measured 20 degrees through holes dug beside the cabin, the airspace beneath the elevated floor maintained 38 degrees. This 18-degree difference meant that heat loss downward from the cabin interior faced a much smaller temperature gradient than in ground contact construction. The floor planks themselves, measured through small holes drilled from below, registered 55 degrees on their upper surface compared to 12 degrees in his neighbor's ground contact cabin on the same night. More dramatic differences appeared in fuel consumption measurements. The carpenter maintained careful records of cordwood use, stacking split logs in measured piles and tracking daily consumption throughout the winter. His elevated cabin required 2 cords of seasoned oak and hickory to maintain comfortable interior temperatures through the entire cold season. His neighbor's ground contact cabin of similar size consumed 3 1/4 cords of the same wood species, representing over 60% higher fuel use for inferior comfort levels. Spring inspection revealed the long-term benefits that elevated construction delivered beyond immediate thermal performance. The carpenter's sill logs, supported on posts and isolated from ground contact, showed no signs of moisture uptake, insect damage, or early decay. Wood moisture content measured with simple tests using small wood shavings showed 9% in the elevated cabin's sills compared to 15% in ground contact construction nearby. The elevated posts themselves remained sound and stable, with no settling, checking, or movement that would compromise the structure's integrity. The neighbor's ground contact cabin told a different story when examined after the same winter. Sill logs showed dark staining and soft spots where moisture had wicked up from stone footings. Carpenter ants had discovered these damp areas and excavated galleries that weakened the structural timber. More concerning, the entire sill system had settled unevenly as frost heave and soil movement affected the stone footings, creating gaps at corner joints that increased heat loss and compromised the building's weather resistance. These measured results validated construction principles that connected immigrant alpine tradition with indigenous American building wisdom, proving that elevation above ground contact delivered concrete advantages in thermal performance, structural durability, and long-term economy despite requiring more sophisticated construction techniques and slightly higher initial labor investment. The elevated foundation solved ground contact problems, but the carpenter soon discovered that heat loss continued through the floor assembly itself. During the first weeks of occupancy in late autumn, he observed that interior temperatures fluctuated wildly between day and night despite consistent fire management. The cabin would warm to 60 degrees by afternoon, but drop to 30 degrees before dawn, creating uncomfortable temperature swings that wasted fuel and disrupted sleep. The problem lay in the floor construction above his carefully positioned posts. Standard frontier flooring consisted of thin planks laid across joists, typically inch-thick boards that provided structural support, but little thermal mass to store and release heat gradually. These thin floors responded quickly to both heating and cooling, absorbing warmth rapidly when the fire burned strong, but losing that heat just as quickly when the fire died to coals. The carpenter recognized this flaw from his immigrant joiner mentor's descriptions of alpine construction, where thick timber floors served as thermal batteries that smoothed temperature variations throughout long winter nights. The solution required a complete reconstruction of the floor system using techniques that combined old-world timber practices with materials available in the Kentucky mountains. The carpenter removed his original thin planking and replaced it with a two-layer system that would store and release heat more effectively. The base layer consisted of standard joists spanning between the sill logs, but above this he installed rough-hewn planks cut from local white oak. These planks measured 2 inches thick and 8 inches wide, providing substantial mass compared to typical frontier flooring. Above the oak planks, the carpenter added a finish layer of puncheon flooring, created by splitting large logs lengthwise and smoothing the flat surfaces with an adze. Each puncheon measured roughly 3 inches thick, creating a total floor mass of 5 inches of solid timber. This massive flooring system would absorb heat from the cabin's fireplace during the day and release that stored thermal energy gradually through the night, maintaining more consistent interior temperatures with less fuel consumption. The installation process demanded precision joinery that few frontier builders possessed. Each puncheon had to be fitted tightly against its neighbors to prevent air gaps that would allow warm air to leak into the space below. The carpenter used traditional techniques learned from his joiner friend, cutting slightly tapered edges on each puncheon so that driving them into position with wooden mauls created compression joints that sealed tightly without gaps. The process required careful measurement and cutting, as each puncheon had to be individually fitted to account for slight variations in log splitting. But thermal mass alone did not address heat loss through the floor assembly. Even with thick timber above, warm air could still circulate downward through gaps between joists, carrying heat into the cooler airspace beneath the cabin. The carpenter needed an insulation layer that would block this air movement while allowing the structural benefits of the elevated foundation to continue. The solution came from the Cherokee elder who had taught him post-setting techniques. The elder demonstrated how his people used natural materials to create air barriers in their elevated structures. Strips of bark, particularly the fibrous inner bark of basswood and alder, could be woven between structural members to block air movement while remaining flexible enough to accommodate seasonal wood movement. The elder showed the carpenter how to harvest bark in long strips during spring, when sap flow made separation easy, then dry and prepare these strips for installation as insulation material. The carpenter adapted this technique to his joist system by installing bark strips in a basket weave pattern between the floor joists. The strips ran perpendicular to the joists, creating a continuous barrier that prevented warm air from moving downward into the cool space beneath the floor. The bark installation required careful tensioning to maintain contact with the joists, while allowing for wood movement as humidity and temperature changed seasonally. Too tight and the bark would tear during wood expansion, too loose and air gaps would compromise the insulation effect. Testing the completed floor system through the winter of 1872 revealed dramatic improvements in thermal performance. The thick puncheon flooring stored heat effectively during the day when the fire burned actively, then released that stored energy throughout the night. Interior temperature measurements showed much smaller fluctuations, with overnight lows rarely dropping below 43 degrees, even when outside temperatures reached -10 degrees. The bark insulation prevented warm air from escaping downward, while the elevated foundation continued to isolate the floor mass from ground cold. Fuel consumption dropped significantly compared to the previous winter. The carpenter's detailed record showed usage of approximately 2 cords for the entire heating season, representing a reduction of nearly 1 full cord compared to his first winter in the elevated cabin. This improvement came entirely from the enhanced floor system, as no other changes had been made to the structure or heating methods. Comparative measurements with neighboring cabins demonstrated the cumulative benefits of combining elevation with thermal mass and insulation. Ground contact cabins in the area consumed 3 to 3 1/4 cords of similar wood for inferior comfort levels. The carpenter's neighbor, whose cabin sat directly on stone footings with thin plank flooring, reported morning floor temperatures of 18 degrees on the coldest nights, compared to 43 degrees in the carpenter's thick-floored elevated cabin. The enhanced floor system also provided unexpected durability benefits. Moisture content measurements in spring showed that the thick timber flooring remained stable and dry throughout the winter, with wood moisture levels around 10%. The bark insulation showed no signs of deterioration, mold, or insect damage, indicating that the system successfully managed moisture while providing thermal benefits. The tight-fitted puncheon surface proved extremely durable under daily use, showing minimal wear or gaps despite the freeze-thaw cycles and foot traffic of a frontier household. Most significantly, the improved system validated the principle that thermal mass, when properly insulated and elevated above ground contact, could dramatically reduce heating fuel requirements while improving comfort levels. The combination of techniques drawn from both immigrant alpine traditions and indigenous American building practices created a floor assembly that performed far better than standard frontier construction methods. Despite the successful thermal mass improvements, the carpenter faced a new problem that emerged during the damp spring of 1873. Even with his elevated floor storing and releasing heat effectively, moisture began accumulating inside the cabin in ways that standard ground contact construction never experienced. The thick timber floor assembly that solved temperature fluctuations created an unintended consequence. The sealed airspace beneath the cabin trapped humidity rising from the soil and prevented natural air circulation that would carry this moisture away. The problem manifested in several troubling ways. Interior humidity levels, measured using simple but effective methods learned from his immigrant mentor, climbed above 60% during periods of spring rain and snowmelt. Condensation formed on the interior walls each morning, creating conditions that encouraged mold growth on clothing, food stores, and even the cabin's log walls. More critically, the stagnant air beneath the floor began affecting the structural timbers. Wood moisture content in the floor joists increased from the dry levels achieved during winter, and the carpenter detected the musty smell that preceded timber decay. The Cherokee elder who had taught post-setting techniques recognized these symptoms immediately when the carpenter described them. The elder explained that his people had faced identical problems when they first experimented with fully enclosed elevated structures. Traditional summer lodges avoided moisture issues because they incorporated deliberate ventilation openings that created controlled air movement through the elevated space. The key insight was that stagnant air beneath a raised floor would eventually become as problematic as direct ground contact, just through different mechanisms. The elder demonstrated the solution using a scale model constructed from split sticks and bark. Traditional indigenous ventilation used a counterintuitive principle. Instead of trying to keep outside air completely separate from the underfloor space, controlled ventilation deliberately introduced fresh air at strategic points while providing exit routes for moisture-laden air. The system created a gentle circulation pattern that prevented stagnation without compromising the thermal benefits of elevation. The specific technique required installing ventilation openings at opposite ends of the underfloor space, positioned to take advantage of prevailing wind patterns. The elder showed the carpenter how to identify the windward and leeward sides of the cabin based on seasonal wind directions, then cut ventilation holes that would create natural air movement driven by pressure differences. The windward opening would admit fresh air, while the leeward opening would allow moisture-laden air to exit, creating continuous but gentle circulation beneath the floor. Implementation demanded precise sizing and positioning to balance ventilation benefits against thermal losses. The carpenter began with 6-inch square openings cut through the floor at carefully selected locations. The windward vent was positioned near the front corner of the cabin, where prevailing northwest winds would create positive pressure, while the leeward vent was cut near the opposite rear corner, where wind flow would create suction. Both vents extended through the thick puncheon flooring and could be controlled using sliding wooden covers during extreme weather. The immigrant joiner provided additional techniques drawn from Swiss mountain construction, where similar moisture problems affected elevated timber buildings. Alpine builders used adjustable shutters that could be opened or closed seasonally to match changing moisture conditions. During wet periods, increased ventilation prevented condensation and timber decay. During extreme cold, partial closure retained more heat while still maintaining essential air movement to prevent stagnation. The carpenter adapted these concepts by creating removable wooden plugs that fit tightly in the floor vents. The plugs allowed fine-tuning of ventilation levels based on weather conditions and seasonal needs. Spring snowmelt required maximum ventilation to handle increased ground moisture, while midwinter cold periods could use reduced airflow to conserve heat without eliminating circulation entirely. Testing the initial ventilation system revealed the need for additional modifications. After 1 month of operation, the carpenter discovered that dust and debris were accumulating in the underfloor space, carried by the ventilation air and deposited when air currents slowed. More significantly, the 6-inch vents proved insufficient for the cabin's size and the moisture load from the surrounding soil during particularly wet periods. The solution required expanding the ventilation capacity and adding maintenance access to the sealed underfloor space. The carpenter enlarged both floor vents to 12-inch square openings, providing increased airflow while maintaining the pressure differential that drove circulation. More innovatively, he installed a removable board panel in the floor near the center of the cabin, creating access for periodic cleaning and inspection of the underfloor conditions. This maintenance access proved essential for long-term system performance. The carpenter could now sweep debris from the airspace, inspect the condition of bark insulation strips, and monitor the posts and sill logs for any signs of moisture damage or pest activity. The removable panel also allowed him to measure air temperatures and humidity levels beneath the floor, providing data to optimize vent settings for different seasons and weather conditions. The enhanced ventilation system delivered measurable improvements in both moisture control and thermal performance. Air temperature measurements beneath the floor showed that the controlled circulation maintained temperatures between 39 and 45 degrees Fahrenheit, even when ground temperature remained at 20 degrees. This represented optimal performance, warm enough to prevent excessive heat loss, but cool enough to create the thermal gradient that drove the cabin's heating efficiency. Interior humidity levels dropped dramatically to around 40%, eliminating the condensation problems that had plagued the cabin during its first spring. Wood moisture content in the floor system stabilized at 9%, well within the range that prevented decay and insect damage. Most importantly, the enhanced ventilation actually improved fuel efficiency rather than compromising it, as drier air required less energy to heat, and the elimination of moisture-related thermal losses offset the minor heat loss through the vents. Comparative measurements with neighboring cabins demonstrated the full impact of controlled underfloor ventilation. The carpenter's neighbor, whose ground contact cabin lacked any systematic moisture control, reported interior humidity levels above 65% during wet periods and fuel consumption that had increased to over 3 cords as moisture-laden air required additional energy to heat effectively. The ventilation system completed the transformation of elevated construction from a simple foundation technique into a comprehensive environmental control system that managed heat, moisture, and structural durability through integrated design principles drawn from both indigenous and immigrant building traditions. The ultimate test of the carpenter's integrated building system arrived during the winter of 1874 to 1875, when an unprecedented cold pattern settled across the Appalachian highlands. Arctic air masses stalled over the region for 7 consecutive weeks, bringing 50 straight nights with temperatures below 0 degrees Fahrenheit. Snow depths reached 4 feet on level ground and 6 feet in drifts, blocking supply roads and isolating homesteads throughout the mountain valleys. Most critically, the sustained cold penetrated deeper into the soil than anyone had experienced, with frost lines extending down nearly 5 feet below the surface. This extreme weather created conditions that exposed every weakness in frontier construction methods, while testing the limits of even well-designed systems. Standard cabins throughout the region faced unprecedented challenges as the deep ground freeze eliminated any thermal buffer that soil normally provided. Families accustomed to burning 2 to 3 cords of wood per winter found themselves consuming fuel at twice the normal rate, while struggling to maintain livable temperatures. Emergency woodcutting parties worked despite dangerous conditions, felling green timber that burned poorly and produced more smoke than heat. The carpenter's neighbor, whose ground contact cabin had shown problems in previous winters, now faced a crisis that threatened survival itself. With sill logs frozen directly to soil that had become as cold as the outdoor air, heat loss accelerated dramatically. Interior temperatures plummeted to 15 degrees Fahrenheit even with a roaring fire, forcing the family to huddle in a single room wearing all their clothing and blankets. Ice formed on the interior walls each night, and water buckets froze solid within 3 feet of the fireplace. Worse, the extreme cold stressed the cabin's structure, opening gaps at corner joints as the ground-frozen sills contracted differently than the upper logs. The neighbors' fuel consumption soared to desperate levels. By the 4th week of the cold siege, they had burned through their entire winter wood supply, plus an additional cord purchased at premium prices from better-prepared families. The need for constant high-temperature fires to combat heat loss meant burning green wood that filled the cabin with smoke, creating breathing problems that weakened the family's ability to maintain the demanding fire schedule. Wood gathering became a daily emergency, with family members venturing into dangerous cold to salvage dead branches and fence rails. In contrast, the carpenter's elevated cabin demonstrated the cumulative benefits of integrated design principles working together under extreme stress. The 4-foot elevation above ground maintained a crucial thermal buffer, even when soil temperatures dropped to match outdoor air. The thick puncheon floor assembly stored heat during the brief periods when sun provided solar gain through south-facing windows, then released that stored energy gradually through each long night. The controlled ventilation system prevented moisture buildup despite the cabin being sealed tightly against extreme cold, while the bark insulation continued blocking air infiltration that would have carried away precious heat. Performance measurements during the coldest week revealed the dramatic differences between the two approaches. While outdoor temperatures held steady at -18 degrees Fahrenheit, the space beneath the carpenter's elevated floor registered 28 degrees, creating a 46-degree temperature differential that significantly reduced heat loss through the floor assembly. Interior temperatures in the elevated cabin stabilized at 52 degrees with normal fire management, requiring no emergency fuel gathering or dangerous overheating of the fireplace system. Most remarkably, the carpenter's fuel consumption remained within normal parameters throughout the crisis. His carefully maintained record showed usage of 2 1/4 cords for the entire severe winter, only slightly higher than typical seasons. This represented less than half the fuel required by comparable ground contact cabins in the same conditions, while delivering superior comfort and safety levels. The integrated system's efficiency meant the carpenter could maintain adequate wood supplies without the dangerous emergency cutting that endangered other families. The crisis created opportunities for direct comparison that settled the technical debate permanently. During the worst week, several neighbors took shelter in the carpenter's cabin when their own structures became uninhabitable. They experienced firsthand the difference between floors that remained warm to the touch and their own cabins where floors felt like walking on ice. The visitors could measure the contrast simply by touching surfaces. The carpenter's thick puncheon floor maintained temperatures around 50 degrees, while their cabin floors registered below 20 degrees. Word of these performance differences spread through the scattered settlement as families shared survival strategies and compared conditions. The county surveyor, who had initially dismissed elevated construction as over-engineering, arrived to investigate after reports that one cabin was consuming half the fuel of others while maintaining better conditions. His measurements confirmed the thermal performance advantages and prompted him to recommend elevated foundation techniques in his subsequent guidance to new settlers. The spring of 1875 revealed the structural advantages that emerged from the severe winter test. Post-winter inspections showed that the carpenter's elevated system had weathered the extreme conditions without damage. The posts remained plumb and stable, the sill logs showed no stress cracking or joint separation, and the floor assembly maintained its tight fits and thermal performance. Wood moisture content measurements confirmed that the structural timbers had remained dry and sound throughout the moisture stress of spring snowmelt. The neighbor's ground contact cabin required extensive repairs after the severe winter. 3 sill logs had to be replaced due to frost damage and splitting where they had been frozen to the ground. Corner joints needed re-chinking where thermal stress had opened gaps, and the entire floor system required rebuilding after frost heave had shifted the foundation stones. The repair costs exceeded $35, representing nearly half a year's cash income for a typical homestead family. By autumn of 1875, 5 new cabins under construction in the valley incorporated elevated foundation systems based directly on the carpenter's proven techniques. The adoptions occurred quietly, without formal acknowledgement of the source, but the technical details clearly derived from observation of the successful system. Posts 4 feet tall, thick floor assemblies, controlled ventilation, and attention to moisture management became standard features in serious construction projects. The transformation represented more than simple copying of techniques. The severe winter had demonstrated that traditional building science, whether derived from immigrant or indigenous sources, addressed fundamental physical realities that frontier expediency could not overcome. Elevated construction required more skill, time, and initial material investment, but delivered measurable advantages in thermal performance, structural durability, and long-term economy that proved essential for sustainable settlement in challenging climates. The legacy extended beyond immediate technical adoption. The carpenter's success established precedents for integrating traditional knowledge with local conditions, proving that immigrant and indigenous building wisdom could be synthesized into systems superior to either approach alone while remaining practical for frontier construction conditions.